All right, so this mini lecture is going to talk about another element in our discussion of circuits, which are affectionately called resistors. So anything that resists the flow of electricity through a circuit is called a resistor. And when we think about what these resistors do, well, they're the things that convert the energy into something usable. So, for example, a light bulb. A light bulb is in a circuit. We have a potential, the thing that we plug into our cord that we plug into our wall. Our wall serves as that potential energy source, or the electricity, of course, into our wall serves that as that electric potential source. Current flows through a closed loop of conductors and lights the light bulb. Across the light bulb, we also have a potential difference. We have that potential drop, the same one that is through the battery that's causing that potential, if it's just the light bulb in the circuit. And so that energy drop is converted to light. Okay, so these elements are what we use in our everyday life, and we are going to collectively call them resistors. So resistors affect the flow of electricity, the flow of current, the flow of charge through a circuit, right? So let's look at kind of some details about resistance, give you a little bit of background on what resistance is, and then we're going to look at an example of what influences the amount of resistance in a device. We're going to use a wire, because even wires have some resistance. Okay, so anything in a circuit that resists the flow of electricity and therefore influences the current is called a resistor. There are certainly other elements we're going to talk about, and the other element, a capacitor, which is slightly different. It's also in a circuit, but we're going to leave that discussion for later. Okay, so a resistor. The resistor is how much it resists, how strong it influences that current, so to speak, is what's known as the resistance. So a little vocabulary today. Resistance is measured in ohms, and we use the capital omega for ohms. So this is the unit of resistance, is in ohms. All right. Current, we know, flows through a wire, and as we've discussed, and even wires have a level of resistance. So we're going to use the wire as an example on what might influence the resistance. Okay, so I'm going to have you think about when you're at a party, okay? So you want to flow from one end of, you get to the party and you want to get to the backyard. So you want to flow from the front door all the way to the back door. What might influence how easy it is for you to flow through that party? Well, if the house is really long, do you experience more resistance or less resistance as you flow through that party? You're going to experience more resistance, right? If we increase the length of a wire, we're using wires as an example, if we increase the length, we increase the resistance. Now, perhaps you know by just sort of your own experience that if you're going to use an extension cord, for example, the shorter the extension cord, the better off you are. If you only have to go a couple of feet, you don't want to get a 50-foot extension cord. Well, it's because we increase the resistance and we have less current that we then can utilize. All right, so there's one example. What else might affect your party? Well, if it's a real narrow hallway, for example, it's going to be kind of hard to get through from the front door to the back. But if there's lots of space, if it's a really wide living room, it might be pretty easy to get from the front to the back, to flow through that house. So if we increase the area, okay, the surface area of that wire, for example, the front area, right, we decrease the resistance. If I make the circle, the wider, fatter cable, fatter wire, I'm going to decrease the resistance. The free electrons have more space to flow through. All right, and then there's actually one more thing, and it's about the material itself. So let's imagine you're at a party with a lot of chatty people, right? Chatty people take a long time to get from the front to the back, versus maybe people who are a little shy, well, then you might get to the back a little bit quicker. So the property of the material itself, and in the case of metals, materials, things that wires are made out of, we call that rho, and it is the resistivity. All right, so this is the property of the material that the wire is made out of. Okay, so different gold versus copper versus silver, different metals, different conductors are going to have a different level of resistivity. So when we put all of this together, we get our equation for resistance in a wire. So R is equal to rho times the length over the area. So this is the resistance in a wire. It's going to be kind of our example to think about what influences resistance in a circuit. Okay, so let's just use this example. Let's just practice using this equation in a relatively straightforward problem just to get a handle on how to manipulate and how to think about what we're reading and how we turn that into our problem. Get my board erased here. Okay. Lots of erasing. All right. So here's what our problem reads. Imagine that you want a really good set of speakers. So you're going to hook your sound system up, or your TV up, up to a really good set of speakers. And the wire must be 20 meters long. So your wire has to be 20 meters long to get from where the TV is, kind of the surround sound in the back of the room. So you need to make sure, so that you can, and we'll get to this in a later lecture, draw a certain amount of current for those speakers. You need to make sure that the resistance in the wire itself is at a maximum of, is at a minimum of 0.10 ohms. I gotta look at my problem. Okay. What is the maximum diameter that we can use for a copper wire? I'm going to use copper. What is the maximum diameter I can get in order to maintain this resistance over that 20 meters of length? Okay, and just because you probably don't have the resistivities in front of you, the resistivity of copper is equal to 1.68 times 10 to the minus 8th ohms meter. All right, so we're going to use our resistance equation for a wire. The resistance is equal to the resistivity times the length over the area. We're interested in knowing what diameter of copper wire we need. Well, that's related to the area, right? So we're going to solve for area. So we can convert this equation just through equation manipulation, where the area equals the resistivity times the length over the resistance that we need. So when we plug that in, we find our resistivity of 1.68 times 10 to the minus 8th times the length of 20 meters all over our resistance that we can't go above of 0.1 ohms. And we find that the area of that cylindrical wire needs to be no more than 3.4 times 10 to the minus 6 square meters. Now we need the diameter, right? So wire is shaped in a cylinder, so we know that the area, cross-sectional area of that wire, is equal to pi r squared. So I can solve for my radius. Radius then is equal to the square root of the cross-sectional area divided by pi. 3.4 times 10 to the minus 6 is that cross-sectional area over pi. And we find the radius of the wire needs to be 1.04 times 10 to the minus 3 meters. That's the radius, and of course we've asked for the diameter. So the diameter, am I too low? No, the diameter is 2 times the radius, which is 2.08 times 10 to the minus 3 meters, or 2.1 millimeters. All right, so just getting comfortable using this idea of resistance, looking at the resistance in a wire and recognizing that resistance is any element in a circuit that impedes the flow of charge. And we're going to find when it does that, it, in combination with the potential, dictates what that current is going to be. All right, good job.